Hey, welcome to Volumes and Integration. What's going on here? What's integration got to do with volumes? Hey, we've done a bit with areas, and let's just review the connection between areas and volumes. And what I'd like you to do is keep a journey going here, right across this top line, and then down the bottom here, and getting a bit more mathematical. And I'd like you to pause the presentation for a few seconds there, and just see if you can see anything developing, areas going into volumes, and then, hey, it's ending up with some integral down the bottom. This is an exciting journey, and what I'm going to do is take you on this journey in a minute. So pause the presentation, see what you think, and then we're going to come back and explore it. Okay, we're back again. Let's start over on the left here. We have an irregular shape there, and we can find its area. And if we give that body some depth, it becomes a three-dimensional solid there. We know that the volume of that is the area of cross-section. I hope you remember this. The area of the cross-section times the height, because we could cut down here in centimetre lots around the body, and every time we cut through the body, the squares that make up the top, there's some squares, not very good ones, as we slice them off, they would form cubes. And how many slices would we make? Each centimetre would be 8 slices, and each of those would produce a cube from every square on the top there. Okay, do you get the idea? Anyway, what about this? This is an area which we could calculate using integral calculus. We did that. But did you work out what's happened over here? What's this circle thing happening here? Well, the circle thing is the rotation of this graph, or all those points on that graph, to 360 degrees, or 2 pi around the x-axis, and we're creating this interesting shape. Okay, so there's quite a few interesting shapes going to come up in this presentation. And then down the bottom here, what's happening down here? Let's just come down a little bit. What's happening down in this one? Hey, we're making up a whole lot of discs. Whole lot of discs here. And you can see they're a different shape. So this interesting shape, come back over here, that we have by rotating that graph around, is not a uniform cross-section. Not uniform in its cross-section. So that's going to pose a problem for finding its volume, isn't it? And then what about this? Did you work out that the volume is approximately the sum from 1 to n of lots of discs? And the volume of those discs is the area of the cross-section, which is always going to be a circle. Here it is here, here it is here. But they're going to vary the area of that circle, which is the cross-section of the disc, times the height or depth of the disc. So this little expression here is summing the volumes of many discs from 1 to n across that integral. Maybe from A to B, we're going to have n discs. And if we did it as n tends to infinity, as we did before with summing the areas of the rectangles, this would be an infinite number of discs. And that should be the total volume, shouldn't it? The same reasoning as before. And how did we do that? Summing an infinite number here of a function times the width. That was proven to be, hey, the integral. And we can now make that not the area giving function, but the volume giving function, if you like. So we need to integrate that. Okay, so it's taking the same maths a step further. Okay, let's do it a little bit more technically down here. And these screen clippings are coming both from Pearson's and from Hayes publications. Okay, well, let's have a look at it. We're looking at discs which have a circular end, so we want the area of that times the width, and let's call the width h. And this is the idea, that we're going to have an infinite number of those discs which have volume, area of their cross-section times the width, which we're now going to change down here. And instead of an infinite number, we're going to say h is tending to 0, and we're going to put as many skinny discs as we can from A to B to get the volume of this rather interesting shape in here. Okay, so what is the area of the end? Ah, look at this. That suggests something. Pi f of x squared. Hey, I know what that is. Let's have a look here. The area of that end, this is a circle. A disc has a circular cross-section. And this would have an area of pi r squared. Only what would r be? R would be the height at point B, let's say, which would be pi f of b squared, okay, because that height there is f of b, or f of x for any point across that shape there. So there it is. The area times the height of that disc, the width of that disc, or the thickness of it, is a volume expression. And we're going to sum n as n tends to infinity, n discs, or that implies the discs are infinitely thin, so h is going to tend to naught. Do you get it? And so here we have it. We're going to integrate from A to B, summing all those discs, just like the areas, summing all the volumes, and then we could put the pi out the front. Just notice that the IB tend to, and this will come up in the formula book down below there in a minute, put it in the formula book like this, but we know from the rules of the definite integral that constant pi can be put out the front. So either way is cool. Okay, are you ready? Let's go and look at what we can do with it now. As we look at this one, we'll just come across a little bit here and have a look. Okay. So here it is, a statement this time from Hayes Publications. When the region enclosed by that function, the x-axis and two vertical lines is revolved. So this is sometimes called volumes of bodies of revolution. Okay, where you create the body by revolving around the x-axis 2 pi or 360 degrees. So we're spinning it around and around and creating this interesting shape. All we got to know is what the function is, and then we're going to say the volume is pi outside of the integral from A to B of y squared, which is r squared. And dx is the thickness which we've just summed over, if you like, reminiscent of that from that limit theory. And here's what the IB produced in the formula book for you. The area formula, the volume formula, and in applications, the kinematics one, the total distance travelled with the absolute value or modulus there. Okay, so let's go and have a look at what we can do. Here's one here from Hayes Publications, and we're going to use integration to find the volume of the solid generated when the line y equals x from 1 to 4 is revolved 2 pi or 360 degrees around the x-axis. So we draw the line and we revolve it from 1 to 4. Hey, that would give us a nice lampshade. Isn't it? That's a lampshade there. Okay, what would be the volume of the whole body, including everything inside there, the volume of that? Well, here's the volume of revolution. It's pi times integral from A to B of y squared. Put in the y function, which is y is equal to x, square it, then we're going to integrate it from 1 to 4, and then times it by pi. So increase the power by 1, divide by the new power, and then evaluate it from 1 to 4. So put in 4 minus 1, 21 pi cubic units. Hey, what have they got here? This is an algebraic check, isn't it? Because we know the formula for the volume of a cone. And our fancy shape, let's have a look at our fancy shape here. Our fancy shape is actually that big cone, here we are, big cone, minus little cone. Can we put dots in here? Big cone minus little cone. And therefore, what is it? A third pi r squared h is the formula. A third pi big cone has a radius of 4 by a depth of 4. Little cone has a radius of 1 and a depth there of 1. Okay, because this is x is 1 and 4. Okay, so it's this little cone has that height, and the big cone has that height. So we can check it. This is a good check on our integral calculus. Only mostly we'll be doing rather interesting shapes that aren't a certain geometric form, or the difference in volumes between two geometric figures there. So we need integral calculus again. Let's go down and have a look at another problem here. Oh, what an interesting shape this is. You get some very creative shapes when the function gets more complicated. So we're going to revolve that from 0 to 5 around the x-axis by 2 pi. So we start with our formula. Volume of revolution is that. Now there's our function, but we still must square it. Okay, so we actually got x to the 4th in there. Don't forget that. The function's already got a square in it because it's this nice parabola there. Okay, increase the power by 1, divide by the new power. Evaluated at 5 minus at 0. And if you do that, you'll get these two numbers, and there's the answer. Now let's do the graphics calculator over here. This is the Casio 9860 Plus again. So how do you do it? Well, you go to run mode. I haven't put all this in. We've seen this in earlier presentations. Run, options, and then calc. And we're going to choose the integral. And you know that that comes up on the calculator like this. We put pi out the front. And then these will be squares that you put the function into. And then square it. Okay. And if you do that, we get 625 pi. The same answer, of course. And we should put down here that it's cubic units. Whatever the units are on the x-axis, that's the unit that we would have as our cube for the volume, or cubing that for the volume. Okay, here's some for you. I know you're dying to have a go. So here's question 1, 2, and 3. Pause the presentation, have a go, and I'll scroll down and show you the answers afterwards, as usual. So now let's come down and come to the next one now. 4, 5, 6. 4 is the opening problem. I haven't shown you that problem. So we'll just go to 5 here. Let's see if we can come up a bit. 5, 6, and 7. Okay. All volumes of solids of revolution is what it's commonly called. Okay, pause the presentation. I'd suggest you do most of these. Have a go. Let's go down and look at the answers now. So coming down, there are our answers, 1 through 7. All right, check them off. Let's go on and look at some others. That's one more little problem down here. Here we have it. And we've got, let's just go up a little bit here. There we are. Example 12. So we're going to have an arch of sine x, there it is, from 0 to pi. And it's rotated 360 or 2 pi around the x-axis. That'd be an interesting shape. Now, to give you a hint here, but let's do without the hint for the moment. Let's go and say this volume of this solid of revolution is pi, the integral over that interval of y squared, because remember a equals pi r squared for the area of that end of those discs. And so putting in y, it's sine squared, and now we are going to try to integrate that. And you know this is a function of a function, and the derivative is not present, so we can't use substitution or reversal of the chain rule. So we've got to change it to this identity, and that's what they were referring to up here. That sine squared is a half take a half cos 2x. From the double angle formula, cos 2x is 1 take 2 sine squared x. And rearrange, that gives here sine squared x is a half minus a half cos 2x. We've seen that before in integrating that function. So let's integrate it. A constant, the integral is that constant times x. Then we've got a half just coming down. The integral of cos 2x. Integral of cos is sine. Cos is friendly under integration. Under differentiation, it gives you minus sine. You've got to watch it there. But this is a function of a function. So reversing that, we've got to divide by the 2. Reversal of that chain rule there. So let's come down a bit and have a look at putting in 0 and then pi. So actually putting in 0 first of all, pi first of all, pi of 2, 2 pi in there, minus putting in naught. Okay, just watch the negative here. We're subtracting the value at pi minus the value at naught. So you need to put all of this in brackets to get the signs right. Here it didn't matter because this bracket came to naught in this particular case. But just remember the use of the minus and a bracket for that second evaluation. All right, so it's pi times pi on 2 or pi squared on 2 cubic units. Are you happy with that? Oh, well, let's see if you are, and we'll come and do some down here. And then we'll finish in this presentation with these two problems. I want you to look at it carefully. Setting out's important. Volume equals pi, integral from a to b of y squared dx, and then putting in your y squared. Okay, pause the presentation and have a go. I'm going to show you the answers now. So let's come down and here are our answers. Okay, so check that out. Now, this is the part 8 of integral calculus, and this is the end of the applications. I'm going to produce another one, part 9, which will mainly consist of problems from Pearson's and the work solutions underneath, so that you can develop your skills straight away there and practice up that whole unit on integration with some review questions. All right, so it's shears now, but I'll see you in that later presentation.